Yes.
of
Yes.
an orthonormal basis. So for usual vector spaces, finite dimensional vector spaces, we know that we have given an inner product, we can find E1, E2, En such that Ei, Ej is delta Ij, and these vectors span and they span, but in the cases that we are working on in analysis, we are not going to, more often than not, we won't have a finite dimensional vector space. So what we are first going to work with is we're going to have an arbitrary family of vectors that are orthonormal to each other. And so you have such an orthonormal set where it's indexed by some general set I. How does one even go about looking at sums of elements in such an orthonormal set? So we have some background before this. So suppose I have a poset. Okay, so this is some topological background to talk about general indexing sets. So suppose I have a poset P such that if I have I comma j in P, there exists a k great, greater than or equal to I and j. We call such a set directed. Okay, and since we don't really need full generality, I'll be working with only a Hilbert space here. So, and then a set xi in where I belongs to P is a net, is called a net. And we have a notion of a limit of a net now. And this xi is a subset of a Hilbert space H. And I have the notion of a limit. So limit xi I belongs to P is equal to x if and only if for all epsilon greater than 0 there exists I naught belonging to P such that for all I greater than or equal to I naught, you have mod of x minus xi less than epsilon. And so note that this is just like what we do for a usual sequence, but now we are not restricted by the fact that P should be a countable set. P can be any set that we want. And so the directed set that we're going to be working with here is, for us, P is equal to Fi. So if I'm given if I have this set Ei, I belongs to I, Fi is the set of all finite dimensional subsets of I. And we know that this will again be a poset. So S1 is less than equal to S2 if and only if S1 is contained in S2. And now S1 union S2 is still going to be finite, and that is greater than or equal to S1 and S2. So this is a directed set, right? And so yeah, okay. So now, yeah, uh, uh, we will talk about now. We say that xi, I belongs to I, as a subset of our Hilbert space. We say that it is uh, if so I'm going to have x of f is equal to the sum of all I belongs to f xi. F belongs to f. I'm going to say that this set is absolutely summable if and only if limit fi, wait, yeah, if this limit exists. The most the simplest thing possible in this case, since we have arbitrary sums, just take finite sums, and if we can find the limit of those finite sums, we'll just call that the arbitrary sum,
You want to take some
where the
norm?
limit.
Don't you want? Don't you want to take some norm or something? You want to talk about absolute summability, no?
um
Don't want to take some norm or something.
so
This is
this is independent of, this is for any finite set, right? So
unconditionally summable. You want?
you just need to take, and this is, yeah, sorry, unconditionally summable. I'm sorry, yeah, unconditionally summable, yes. And so unconditionally summable. And so now suppose I have an ortholemma, okay? The following are okay. Before that, we also now, I have a notion similar to what we had for limits, since we are working with a complete normed space. I have the notion of a Cauchy limit. So f belongs to fi, xf exists if and only if, for all epsilon greater than 0, there exists f naught belonging to fi, such that for all equal to f naught, uh, note that one direction, that if the limit exists, then we are going to have this condition just by the proof of the usual limit, where I'll take the f naught such that uh, if x is the limit, then x minus xg plus x minus xh, I can write that this term is going to be less than x minus xg plus x minus xh. minus xh. And so if I can make that less than epsilon by 2, both of those terms, I will get that this entire thing is going to be less than epsilon. And so one direction follows from the usual limit notion. For the other direction, now, since we have that it is finite, I can just, since we have that our space is complete, I can actually get some Cauchy sequence in this thing. So if I can get a sequence f1 greater than f2 greater than or equal to f3, such that for all I comma j greater than k, mod of x fi minus x fj is less than, say, 1 by I. And now, if I have this condition on the LHS, and so now I have a Cauchy sequence, and if this limit is x, if this limit is x, I can do the same thing where if I take for all g greater than or equal to f2i, and I can take this xg minus x is less than or equal to mod of xg minus xf2i plus mod of xf minus x. And now this is going to be less than 1 by 2i plus 1 by 2i, which is equal to 1 by I. And so this limit of the general Cauchy sequence that I got, the specific Cauchy sequence will be the limit for all of these things. So I just have this particular thing. And now, if I have and so yeah, we'll move on to the lemma, which is and more specifically, now when I have this condition that sigma, so if I take the condition can be rewritten as, since we are working with sums here, that for all g greater than or equal to f naught, I have xg minus x f naught is less than epsilon, but g and f naught is contained in g, and so I can just write it as g intersection f naught complement is less than epsilon. And so I can have another condition that the limit exists if and only if for all epsilon greater than 0, there exists f naught belonging to f of I, such that for all g belonging to f of I minus f naught. Now I minus f naught is basically finite sets that are disjoint from f naught. This should be less than this should be less than epsilon, and this is the condition that we are going to be using for the lemma. And so the following are equivalent. 1. So I have a set alpha I belongs to I, and so uh, alpha ei, and alpha are complex numbers. Ei is an orthonormal set, and is unconditionally summable. Three. Sigma I belongs to F.
So what do you think? How many more days? No music. Okay.
Is sigma alpha square is where F belongs to Fi is finite, and for there exists x naught which belongs to the closure of the sum of ei such that what this is give us, this is now going to be a maximal orthonormal set, which means that it's not contained in any other orthonormal set. And so note that if I just have alpha and if I have x in my Hilbert space, and I can think of alpha as x comma ei, and by Bessel's inequality we know that these finite sums are all less than the modulus of x. And so I'm going to get this generalized projection of, I'm going to get an x naught in the closure of the sum such that x comma ei is equal to x naught comma ei is equal to x comma ei. And additionally, if this set is maximal, I must have that x is equal to x naught, because otherwise then I could just take the perpendicular vector as in x naught minus x upon the modulus of x naught minus x, and that would now be perpendicular to each of these ei's, and I could just introduce that into the orthonormal set, and so that would be a contradiction. So note that this lemma essentially is going to give us that for a maximal set, the entire span is going to be the Hilbert space H. So 1, if and only if for all epsilon greater than 0, there exists F belonging to Fi such that mod of, so I'm going to write mod of xf, where xf is just what we defined before, is less than epsilon, where xf is equal to sigma and if and only if for all epsilon greater than 0 there exists f belonging to fi such that okay, sorry, I wrote only half the statement. Yeah.
And how are they feeding her then?
For all G belonging to f of I minus f naught. Right. As in, yeah, there exists such that mod of, I can just replace this by the square, is less than epsilon. For all, if and only if, for all epsilon greater than 0, there exists f. But note that because it's an orthonormal, it's going to be
I'm not so good at this. I always forget what I need, so I don't recollect. But I think it's carbon dioxide.
because it's in general going to be alpha I, alpha j, but then the coefficient is delta ij, and when I is not equal to j, it's 0, since it's orthonormal. And so you have this less than epsilon. So you get this condition. And now note that this is the same condition as this thing being summable. Sigma, the set mod alpha I square being unconditionally summable. But note that this just means that if and only if for all epsilon greater than 0, there exists f belonging to fi such that sigma mod of is less than epsilon plus. So I'm going to write af is less than, okay, I rather than introducing notation, I'll just write it down, is less than I belongs to G is less than, and now I'm just replacing this by for all G belonging to f of I, right? Till here it's just for them disjoint from f naught. And this just means that this set is bounded above and that the supremum exists. And since it's bounded above, this set is going to have a supremum. And so the first three we get 1 if and only if 2, if and only if 3. And now we just need to get this fourth one. And so if this is summable, if it's unconditionally summable, one implies x, if I put x naught is equal to limit xf, f belongs to fi, then since it's all continuous, I can just go to x naught. Xf comma ei, and now again this is a finite sum, and so we have and so this sum is finite, and so this is just going to be alpha I, because this is either going to be alpha I or it's going to be 0. And in terms of the definition, for all f greater than the singleton set alpha I have and disjoint from it, I have this set is going to be for all things greater than alpha I, since it contains alpha I, it's going to be xf comma ei is going to be alpha I, and so the limit is going to be alpha I itself. And so 1 implies 4, and if I have 4, more importantly, by Bessel's inequality, I have mod of x naught is greater than or equal to where I is in F, right? And so this is bounded above. Sorry, this is bounded above, and so 3 also holds. So we have that all of these are equivalent. Right. And now for the main theorem, the following are equivalent. EI is a maximal set for all x belonging to H, x is equal to uh, x comma EI yeah, and 4 for all sorry, for all x belong to H, I have
Not like that. I'm not
whole square. And now, okay, so one implies two, as we said, is obvious. So if x belongs to H, we know that by Bessel, x comma EI square is absolutely summable, is unconditionally summable by Bessel, as we said before. Since any finite sum is, more specifically, this is upper bounded by mod of x square by Bessel's inequality, and so since it has an upper bound, it is unconditionally summable by the equivalence that we've seen. And so there exists an x naught belonging to H such that x naught is equal to, and now if x naught is not equal to x, I can take x and note that this is going to be perpendicular to each of these, and so x comma EI is equal to x naught comma EI is perpendicular to EI. And so contradiction. since introducing this other vector into this would still be an orthonormal basis. And so 1 implies 2 is clear. If we have 2 implies 3, we have x is equal to sorry, this should be ai, and y is equal to sigma and so is equal to, I can just take the limit of finite things. But note that this limit is just going to be f. Again, now since we have the orthonormal basis, it's going to be sigma, which is just going to be sigma since we know that y comma ai bar is equal to ei comma y, where I belongs to I. And so 2 implies 3. And 3 implies 4 you get by putting x equal to y. Put x equal to y. And 4 implies 1. You get because 4 implies 1 is because now if uh, you have ei where you have I union j, and if j is not equal to phi, you sigma 0, and if let j where j is not in I. Okay. Right. As in, I've taken a bigger orthonormal set, and if of them, I have this formula from 4, and so, but all of these are 0, and so I'm going to get ej. Oh, sorry, this should be square. And so, this is what we get, contradiction. And so 4 implies 1. And yeah, set generates arbitrary sums, and I have this arbitrary projection. I have the what was usually a finite sum has now become an arbitrary sum over an arbitrary indexing set. Okay, that's it from my side. Does anyone have any questions? Okay. Yeah.
I think it's fine. So Okay, I will stop recording.